We are now moving on to our next spotlight speaker, Dr. Pierre Gentine, the director of the Learning the Earth with Artificial Intelligence and Physics Center here at Columbia University, who's going to talk a little bit about GeoAI and climate. Pierre?
Right. Thanks a lot for having me today. I wanted to talk a little bit about some of the excitement that's been happening in the field at the intersection between geosciences and AI. Starting with that, this is some results from colleagues at Google, where on the left-hand side, you have kind of the global truth of like some moisture field across the Earth. This is for like weather forecast. And on the right-hand side, you have kind of an AI-based weather forecast. And basically, the main point is they look very, very similar. So we were just talking about breaking the laws of physics, but in many aspects, those AI-based models tend to be better than physics-based models. So that's actually a huge, huge development over the last couple of years. I wanted to start as to why the geosciences are a good place to use AI. The main point being that we have a lot of data. We tend to be in a very wealthy environment in terms of satellites. We have many, many constellations of various satellites observing various parts of the Earth with optical sensors, microwave sensors, radar and LiDAR, and whatnot. We also have many, many simulations, from global simulations of the whole climate over like century time scales, all the way to very detailed fine-scale simulations representing all of the turbulence, such as clouds in the atmosphere. So we really have a diversity and wealth of different types of data and data sets. All the way also on the right-hand side, so this is for weather station data, but we also have a lot of in-the-ground, on-the-ground type sensors, so in-situ type sensors. And kind of the challenges, and that's kind of the power of AI for that, is that it's been very difficult up to now to actually put all of those things together, right? So it's been typically an afterthought. We were using one sensor at a time. But the main point is we actually want to think of that as what people are doing for AI. You can think of that as text, images, and videos, what we call typically modalities, and you would want to fuse that. That's the whole concept of what we call foundation models. So you could think of that as different modalities, so different types of data, and we want to fuse them. Over the last couple of years, we've really witnessed, so that's what I was mentioning before, we've been witnessing a revolution in terms of AI-based weather forecasting. That really got started back in 2018 by Peter Dubin and Peter Bauer back at the European Center for Medium Weather Forecast, where they had basically a prototype, and they were comparing that to the state-of-the-art physics-based model, which is here at 100% in green, again from the same European Center Medium Weather Forecast model. And what they could show is that they were actually way below that back in 2018. But over just a couple of years, many, many groups, including many in the private sector, Google, NVIDIA, and DeepMind in particular, have been able to actually push the limit of that and have been able to basically surpass physics-based models. So the AI-based models now are outperforming weather-based models. And it's not just the performance and the accuracy, it's also the speed. We are running them at basically orders of magnitude faster than the original models. And that's really transformative as well in terms of the applications. Roughly speaking, if you have a performant laptop, you can run those AI-based weather models on your laptop, and therefore you can think about many, many different applications from renewable energies and so on and so forth, or extreme weather detection. And this is an example here from the model from DeepMind. Again, you have a global truth on the left-hand side, looking at some particular field, and you can see the forecast on the right-hand side. And some of the earlier models tended to suffer from this kind of blurriness or fuzziness that was appearing over time. They were skillful in many aspects, but they were becoming a little bit physically unrealistic. And basically, over the last couple of years, basically the last 2 years, that's been solved, and that's basically what I showed you before. On the right-hand side, again, this is an example from Google, but you have many examples now that are actually really extremely performant. And what you can see is that those models really can very, very nicely replicate the physics of the atmosphere, and again, better than so-called physics-based model, because they had many knobs that we couldn't really tune at scale using data. So they are extremely performant, and again, at a fraction of the cost of the original model. So that's really transformative. In parallel to that, there's been quite a bit of development on the climate space. So that's been very much what we've been doing at the LEAP Center, but also with colleagues around the globe, and trying to push also the capacity of those climate models that are looking at long-term, typically projections, so 10-year plus, and trying to improve the quality of those models. And this is an example here looking at the distribution of precipitation. So when you go to the right-hand side, you have more and more extreme rainfall. And standard models, such as the one in green here, which are very, very typical climate models, tend to actually very much miss the extreme events, right? Intense rainfall. And that's highly problematic because that's kind of the core of the game. We would like to actually predict those extremes and how they are changing in a changing climate. And what we could see is that using machine learning, we could actually be on par with really, really extremely detailed simulation at kilometer scale, even though we would run that at just a fraction of the cost. So we could see that we could, again, very similar to what I showed you for weather, we could actually do a much better job, especially for things we care about, so not just the average behavior, but even also for extremes. So oftentimes we think about machine learning as not being so great for extremes, but in that particular case, it works very well. We could also show that we could resolve many long-standing biases. So we tend, historically, if you look at weather forecast and climate prediction, there's typically a bias in terms of when we actually tend to have rainfall during the day. This is over the US, and you can see, again, in red, typically you have this bias where most of the rainfall is happening in the early afternoon. And what we could show is we could largely solve that bias, and we could actually get 2 peaks in rainfall, which is, again, a long-standing bias. And again, using machine learning, we could very nicely replicate a much more physically realistic type behavior, even though those models at the bottom are so-called physics-based. In parallel to that, there's been also a lot of work over the last couple of years that was actually just mentioned a couple of minutes ago in terms of using AI for like full emulation. So I showed you that for the atmosphere, but a lot of colleagues, including folks downtown at NYU, good colleagues, Lorzana and colleagues, they've been looking at also emulating the entire ocean and coupling that to the atmosphere. And that's being used, for instance, to push the envelope, for instance, for sub-seasonal to seasonal forecast, but also to think about the long-term behavior of the ocean. And again, those simulations can run at a fraction of the cost of the original model, at least 100 times faster, if not more, almost 1,000 times faster. So that's, again, transformative. We can start thinking about many, many realizations, and therefore trying to poke many of the extreme events that we are so interested in, but also thinking about the long-term behavior of the ocean. So that's really transforming how we can approach those so-called simulations type. In parallel to that, there's been a lot of development as well where we've been seeing a merging between the machine learning and AI tools and what we've been historically been doing in weather forecasting, which is so-called data assimilation. Data assimilation means that you typically have a physics-based model and you want to use observations. So every day you do your weather forecast and you get new observations and you want to fuse them and merge them in the best possible way. And what we've shown is you can think of that as prompting, right? Very similar to what we do when we want to generate an image, right? You say, I'm prompting something, I'm saying something, and I will generate an image based on that prompt. So for instance, you want to have a picture of a cat on Broadway. And this is very much the same. We've said that we can use the exact same tools, so generative AI and so-called diffusion models, to basically generate a forecast of the weather tomorrow by the prompting, and the prompting being the weather forecast that we had the day before, and also the observations. So we can really frame that very much within the generative AI context, and we can show that we can improve the performance, and we can, again, do that at a fraction of the cost of the original algorithm. So that can also push the envelope of not just the modeling side of things, but how we also fuse observations with the models as well. There's also a lot of excitement these days in terms of not getting just at the coarse resolution. So climate models and even weather forecasting can be at a relatively coarse resolution. So climate models tend to be at hundreds of kilometers, weather forecasts at a couple of kilometers. But oftentimes we need information at a much finer resolution, right? If we are at 100 kilometers, we cannot think about tropical cyclones, for instance, but that's typically what we would want to forecast or project into the future. And what we showed is we could actually use, again, those generative methods, and you can think about that, again, as prompting and trying to do image generation when we want to generate like a fine-scale field, like wind field or rainfall pattern, and trying to think about that as a way to say, can you predict at fine scale resolution the evolution of tropical cyclones into the future? And you can actually use that for like impact and thinking about adaptation and resilience to changing extreme events. So that's really transforming the way we've been doing that, and you can have many samples the same way you generate different images every time you prompt. With the same prompt, you can generate different samples, and we are doing the same thing here, different wind patterns or different rainfall patterns. In parallel to that, there's been a lot of development in using AI for like monitoring in particular. So this is an example here for something quite impactful, like wildfire near real-time monitoring, where we can use AI and a vast suite of satellite imagery to actually map out the evolution of a wildfire, and people can actually also use that as a predictive tool to see as to where the wildfire is going to evolve as a way to potentially evacuate and provide early warning system as well. So that's really, again, transforming this capacity to be almost quasi-near or near real time, which was really a struggle back even a couple of years back, right? We had to do all of this data analysis. It was complicated. And now we can actually use a lot of the innovation that's coming from computer vision and bringing that to the geosciences to directly have like quite impactful and meaningful work for real-world applications. Another like very similar type of work that's been done is looking at floods. So recently people have been using different types and suites of satellite to actually start looking at floods and also mapping out their evolution over time. So regions over which we are seeing more and more extension of the flooding flood zone and regions where we see a decay. And again, that's a place where we can fuse different types of satellite, which used to historically be a challenge, and now those tools are a lot more flexible and agile to those different types of data sets. So that can really transform the way we are actually monitoring risk in particular. There's been a lot of buzz over the last couple of weeks or months in terms of some work by colleagues at DeepMind, where they've been releasing this so-called alpha Earth. So you most likely have heard about alpha folding for protein unfolding. And then what they've shown is that we can basically take all of the different observations of the Earth, so many different types of satellites and observational products that we have, and we can basically embed or compress all of that into only 64 pieces of information, so in a vector of size 64. And that can be used to do many different things, to do like monitoring over time, to look at how photosynthesis is evolving, how land use, land cover change is evolving. And basically all of this very complex information that we had across many different satellites, we can basically compress that information and get that into only 64 basically different dimensions. And that's really transformative to start thinking about the evolution of the Earth and the evolution of the landscape and how that's changing across different timescales from a couple of days to a couple of years and really poking the Earth to a large extent. So that's really transforming the way we are monitoring the Earth. Wanted to conclude to start thinking about, there's really, so there's been a lot of development, especially using generative AI and foundation models. So that's been a lot of what we've seen over the last couple of years. But I think we should really be aware that kind of the next revolution is going to be agentic, right? So we are going to have agents with which we can actually interact. They can actually locate data. They can actually find the data for us. They can do some simulation. They can also run some analysis as well. And this is an example with collaborators at Shanghai AI Lab, where we actually showed that we can use this type of platform to actually extract data, perform scientific innovation, and try to actually basically provide a lot of support to scientists to accelerate the science that we do. In parallel to that, this is some work from colleagues at University of California, San Diego, Rose Yu and Duncan Watson-Paris. They've been showing kind of the same for weather, where you can actually have questions. You know, for instance, you would want to say, I have this data, and can you tell me whether I will have an extreme event tomorrow? So that's directly the prompting that you have. And then the agents will actually locate the information, analyze the data. They can even run scripts and run simulations to potentially refine the type of forecast that we are doing. And that's really transformative because that's really kind of a dialogue, much more like a language. And that really reduces the barrier that we have to actually directly get the answer to what we want to do. And that's really transforming the way we are doing not just science, but how we are also communicating the science and how people can actually use those tools. So the tools are all in the background, but the interaction and in the interfacing is actually much, much simpler than what we've seen in the past. So to conclude, AI is really, I think, transforming, if not revolutionizing, the geosciences. We are seeing a lot of innovation in terms of how AI can actually improve the quality of simulations, how we can actually also accelerate simulations, such as for the atmosphere or the ocean, for weather, all the way to short-term climate prediction, but also in the way we can actually merge data, right? That's been historically really challenging. We had those different modalities or different types of data, different satellites on different platforms, and now we can actually use those things and we can actually ingest that at scale and potentially even compress that, as to the example I showed you before, on only 64 dimensions to really understand how the Earth is actually changing in quasi-real time. And that can really improve the physical modeling of the Earth, and that's for any type of application, from like landscape assessment for the geosciences, but also for weather and climate altogether. In terms of observations, we can really see that AI is a very, very powerful tool to actually extract complex structure, compress information into what we call embedding or data compression, and also merging those data sets. So that's the whole concept of what we call foundation models. We have different types of data, and we want to merge them into the similar same embedding, right? So that's some sort of data compression, but like a smart data compression, if you will. And that really helps actually better understand and monitor the Earth, right? Because we are in this compressed world, we don't need to carry all of the different pixels and all of the information. We can actually track that in quasi-real time. And finally, I think, and that's going to be a really important development over the next couple of years, is that AI is really accelerating how we do science. And that's true for the scientists, but that could be also true for businesses as well. And that can really replace many of the routine tasks. It used to be really cumbersome to actually locate some particular satellite product, find the particular data. So for instance, if you look at NASA, for each individual mission, they had a different portal. Now we can actually use a lot of those tools to actually search that, look that up, and analyze the data. And that can really simplify and accelerate, especially many of the routine tasks that we have, such as data downloading and data merging all together. And that, I think, will really accelerate science altogether, but also many of the applications for the industries in particular. Just to wrap up, to think a little bit about the future, I think soon AI will do much more than that. We are starting to see, we are actually working also in my group on how AI can actually do new discoveries, new science discoveries, and we can see that AI can sometimes propose, when it has access to scientific literature, a lot of the existing data, it can propose new ideas, and some of those ideas for now are already interesting, right? And most likely in the next couple of years, we are going to see a lot more evolution there. And then the question is, for now, it's actually supporting scientists, but maybe, and that's a little bit my fear, I would say, is that maybe at some point, especially the entry-level scientists might be partially replaced. So that's something we should be prepared for. And we need to think of ourselves, how can we be architects and use those tools to really accelerate progress and innovation, and how do we actually integrate them, whether that's for businesses where we have agents along with employees, or within the science world where we have, for instance, agents and PhD students. So with that, happy to take any questions. Thank you. There's time for questions.
Hi, Michael Mann, George Washington University. I think that one of the challenges that I've found with some of the sort of embedding techniques, I guess I'm more familiar on the remote sensing side, is that, for instance, Google's embedding techniques often don't perform as well as sort of a more refined set of, highly tuned model inputs. And I guess I'm a little bit concerned in that when we do this sort of embeddings, we're quite likely to start finding sort of spurious correlations, and I think particularly maybe with your work, where you have huge amounts of sensor data, and if you sort of lose that connection between the inputs and the outputs through this embedding, through the compression, how can you tell whether you're just looking at sensor drift or I mean, I know that the target outcome is like, okay, it's performant, it's doing a good job, but shouldn't you be able to look under the hood and figure out, okay, why is something going wrong? How do we do that in this new space?
That's a great question. I'm actually very interested in that. I think it's a trade-off, right, when we think about those embeddings. So when you go to 64 dimensions, for instance, there's a very, very high level of compression going on, right? But if you want to go for more like predictive power, typically you will need to actually compress, but keep like the compression relatively low, right? Almost like lossless compression to a large extent, right? What that embedding does, even sometimes you barely have any type of compression, but what typically that, if you look at the embedding, what it typically does is it tends to actually decorrelate a lot of those variables. And that's the big advantage as opposed to many of those variables that are extremely correlated, right? So to give a concrete example, we looked at data assimilation. We had this embedding, and we were doing data assimilation in the embedding, and what we could see is that it's actually a lot more performant. And the performance was coming from the fact that the embedding by construction was trying to decorrelate many of those different variables. But it's a trade-off, sorry, between predictive capacity, where you need to have high dimension. I mean, there's no like free lunch. And I would say understanding, right? So the more you compress, the more you understand. I mean, I cannot really go beyond 3D, you know, and most humans can't. But if you have already like hundreds of dimensions, that becomes really difficult to understand, I would say.